And the next one is a mix of experts. And as I said, many people don't put this mix of experts in Ensemble Learning chapter. But I think this is the perfect chapter where we can put this mix of experts. Okay, so we have multiple experts like this, like M models. And then these experts divide a problem space into several subspaces. Okay, so think about this mix of Gaussian. This mix of experts is different from mix of Gaussian, so I'm going to talk about the difference later. And the Bayesian models work locally for a given task, like this. So this is what we want, right? So this one is input and this one is output. So based on this probability, we can classify. And this one can be decomposed into several probability in this way. And each one can be decomposed into the local model and the gate. So this one says, given this x and with this weight, then what is the probability? Okay. And then gate says, given this x, what is the probability of this weight? Okay. So we put this gate on the local models. Okay. So look at this one. This one is a mix of Gaussian. So we have a probability here and we have a pi, which is the weight of this distribution. But this pi is not a function of the x. Okay. But in the mix of experts, this gate is a function of x. So input x goes into the expert. And also it goes into the gate network. And then we have m outputs from n experts. Then we multiply this gate weight on these outputs. And then we make a final decision. Okay, and then gate network regulates where the Bayesian model should work. So it can be implemented as softmax of the function g sub I. Okay, and g sub I can be simply a linear model. And then the expert P can be modeled by Gaussian when the y is a linear model of x. So that P of y is a Gaussian distribution. So we have two models. Y is w sub 1 times x and w sub 2 times x. These are kind of expert. And then we have a gate for the first model and the second model. And when the first model is more dominant on this range, then we have to use this model. And when the second model is more dominant, then we can use this model, more importantly. So the gates define the location, the area of the experts, the local model. And the local model will work on that area. So this one is slightly different from the bagging or boosting, but still we have lots of models and these models are working together and they are combined to make a final decision. So that's why I put this mix of experts in the Ensemble Learning chapter. And the training is based on the EM algorithms. So as you can see, these equations look quite similar to a mix of Gaussian. So as we used EM algorithms to train the mix of Gaussian, we use the same algorithm to train the mix of experts. But when we drive the EM algorithm, the equations would be different. Okay, but basically we use the same type of algorithm. Okay, then the next topic is why ensemble learning works. Okay, based on the two observations, ensemble learning works. First one is that ensemble learning reduces the variance. Okay, so we talked about the variance and bias trade-off in the density estimation, right? So in error, we have a variance and the bias. So ensemble learning can reduce the variance or it can reduce the bias. So when we use bagging especially, then the average of diverse models reduces the variance without affecting bias because each model can be trained with the same kind of training algorithm. Okay, so each individual model has the same kind of variance. But since we are taking average, then the variance decreases. So it reduces the sensitivity of individual data points. So it's more robust. So finally, it minimizes the error. Or, especially when we use boosting, we can reduce the bias effect. For some simple models, average of models reduce bias without affecting variance. So remember when we train the models in sequence, the next model depends on the previous models, right? So when the previous models are not working perfect with some specific examples, then the next model will focus on those models. So the model is actually increasing kind of expression power to minimize the error. Okay, so as I said, we can increase the capacity, computation power with more models and control variance by fitting one component at a time. So we are not actually increasing the variance because we train the models with the same kind of training algorithms. But since we are focusing on some specific samples, so we can actually increase the capacity. So when we have more models, then all these models are focusing on some different samples, so that in total we have a more kind of complex model to talk about a lot of different kind of variations in the data samples. So we can reduce the bias. So either we reduce the variance or bias, we can actually minimize the error. Okay, so we talked about this bias variance trade-off in density estimation, but here is kind of review here. So in density estimation, we focused on the parameters, okay, instead of function and the output of the function. We just focused on the parameter theta per se. But here, we are interested in the model and the output. So this is the perfect model, ideal model, okay? And when we decompose this error, this one is label and this one is estimation, then this is an error, expected error. And this one is the variance of f hat. F hat is our model, and this is the bias of f hat. So this one says our model is not perfect, and this one says our model is too sensitive to some data samples. So either we can reduce this one or this one with Ensemble Learning. And as I said, variance is sensitivity to small fluctuations in the training set. And the bias is erroneous assumption in the model. So when the model is not right, then we have large bias. Okay, so this slide summarizes how bagging and boosting works, and basically how ensemble learning works here. So this is quite important. All ensemble algorithms encourage diversity. So here's a saying by Einstein: when all think alike, no one thinks very much. Think about your meetings. And in your meetings, we have, let's say, 5 people in your meeting, and all these 5 people, they think in the same way. Then what is the point of having meeting? So when we have a meeting, to make the meeting more productive, then we need more different kind of ideas and the thoughts and different concerns. Sometimes we have conflicts, but that's how we make a progress. So the algorithms, the individual classifiers should be different. Then we can improve the performance. So as I said, in the bagging we reduce the variance, and in the boosting we reduce the bias. And in the bagging, all the models are supposed to be uncorrelated. And in the boosting, all the models are kind of complementary to each other. So when the first model is not working for these samples, and the second model can work for those specific samples. Okay, so they are complementary to each other. And the base models should be different and complementary. This is quite important message. So here is a final note about this ensemble learning. When you have a model, it could be KNN or night-based classifier and deep neural network, whatever. When you have a model, then we can have M models, okay? Then we can combine simply like a bagging. Then we can improve the performance. At least ensemble learning will have the same performance or slightly better performance all the time. But the important thing is that we have to make the classifiers different. So when you train the first model, then the second model should be different from the first model. How? It could be based on the different training set, or it could be based on different initializations, especially when you use the deep neural networks. Then we initialize the parameters randomly. Then that would work. When we initialize the parameters randomly, then the first model's initial parameters and second model's initial parameters, they are all different. Then they will converge to a different local minimum. Okay, even though their performance will be similar, but still they are different models. And then if we increase the number of models, then we can improve the performance. So always, if you work in a company to build up commercial product, then you have to think of ensemble learning all the time, as long as the computation cost is not a big deal. Because when we have multiple models, it increases computational cost. So if the speed is not the problem and the computational cost is not a big deal, then you have to think about ensemble learning. And when you use ensemble learning, you have to think about how to make the models different. And if you are in academia, then it's a little different. Since we all know that if we use ensemble learning, then we can improve the performance. Okay, that's ensemble learning issue. So when we work in an academia, then we can focus on one single model. Then we can compare the single models. That's a fair comparison, okay? But as I said, if you work in a company, then the goal is to improve the performance. So it's not just a fair comparison, okay? The goal is to make a better model. So you have to think about ensemble learning all the time. Okay, now we have a couple of applications. Face detection. In this case, we use a simple weak classifier first because we have a lot of face images. Then if we apply a deep neural network, really complicated, complex model every time, then it takes too much time. So first we use a simple classifier really quickly. And then if the weak classifier says, oh, this is a candidate, there might be a face, then we apply more complicated neural network. So that is kind of boosting. Okay, first we apply the weak classifier, and then if there is a possibility, then we apply the complicated model so that we can have a fast and accurate face detection model. And the next application is Netflix Prize. There was a competition in Netflix, and it's basically a film recommendation. And there was a winner, and in interview he said, our experience is that most efforts should be concentrated in deriving substantially different approaches. As I said, in ensemble learning, we need different models. So substantially different approaches rather than refining a simple technique. So he used a lot of models and he combined. So basically he used 107 models for ensemble learning. Okay, and the next application is image classification. So in 2011, when the deep learning was not that hot topic yet, these guys applied the committee of deep learning. Okay, CNN is a deep learning algorithm, and they applied a committee. It is actually ensemble learning. So they applied a committee of CNNs, and the accuracy of German traffic sign recognition is better than human performance. Okay, actually this is the first kind of successful story for deep learning. And this is another application, machine translation. So in machine translation, if we use a single model, the performance is like this. And if we use 4 different models, then look at these numbers. Every time it is improving the performance. So it's almost 1.2 point something. 2 point something is a significant improvement. Okay, so all the numbers are encouraging. And Google Machine Translation has 8 models for Ensemble. So in Google Neural Machine Translation, each model is huge. And then they have 8 models.